Good day from Chem Help ASAP. This video provides practice problems for determining the products of addition reactions and related chemistry. The problems in this video are a bit more challenging and best suited for students who are at the end of their first semester of organic chemistry. All of these problems have been pulled from reviews of chemical literature on synthetic reactions used in the pharmaceutical industry. Citations are on the slides. Check the video description to find links to printable copies of these problems and their solutions. There will be links during the video that will connect you to other videos that provide more detail on these types of reactions. Alkene addition reactions are a standard part of introductory organic chemistry and typically covered in Organic 1. There are many ways to classify alkene additions. One common method is based on the stereochemical outcome of the reaction. On the screen we have a hypothetical addition reaction. We are adding XY to an alkene. Note that there are two products shown. If both X and Y add to the same face of the pi bond of the alkene, then we get this syn product. If the reaction mechanism only generates the syn product, then we call the reaction a syn addition. If instead X and Y add to the opposite face of the alkene pi bond, then that is the antiproduct. If the reaction mechanism only gives the antiproduct, then we call it an anti-addition. Some addition reactions give a mixture of syn and anti-products, and these reactions are neither syn nor anti-additions. Note that these two reaction products, syn and anti, are stereoisomers of one another. They are diastereomers. Therefore, stereochemistry is an important aspect of alkene additions, and we'll talk about stereochemistry quite a bit as we work through the reactions that follow. One additional comment before we move on: the reactions in this video were pulled from synthetic routes of approved drugs. While you may learn many different addition reactions in organic chemistry, the number of reactions that are regularly used on large scale to make pharmaceuticals is somewhat smaller. Therefore, there isn't a huge variety in the reactions in this video. Okay, with that said, let's get started. Reaction number 1. Over the arrow we have hydrogen and palladium on carbon. This looks like a hydrogenation. Sure enough, our starter material has an alkene. This is definitely a hydrogenation. These are typical hydrogenation conditions: hydrogen, PDC, and an alcohol solvent. This is a metal-catalyzed addition of hydrogen to the alkene. The metal is palladium. Palladium on carbon is palladium embedded into graphite, which is like soot, black soot. So PDC looks like black powder. You mix it with your alkene and the solvent, and the whole reaction just looks black. After adding hydrogen, and once the reaction is done, you filter away the black powder and evaporate the solvent, and you normally get a very clean addition product. These are great reactions. Here is our product. So in this reaction, we have gone from having 2 hydrogens on the alkene to 4 hydrogens on the alkyl chain. It is an addition of hydrogen. Typically, hydrogenations add hydrogen to alkenes, but the CC pi bonds of aromatic rings, like this benzene ring, are not touched by the reaction. Problem number 2. Look over the arrow again. We have hydrogen, palladium on carbon, and ethanol, an alcohol solvent. This is another hydrogenation. We need to look closely in our starting material, but here is the alkene. This alkene should be gone in the product. Sure enough, the alkene is gone. We started with 1 hydrogen on the alkene, and now we have 3 hydrogens on those 2 carbons. How about the stereochemistry? Why is the hydrogen shown as down. Why not up? It's hard to answer without having more experience with this particular type of molecule. It's possible that this methyl group is sticking up and blocking the top face of the alkene. The hydrogen therefore adds from the bottom face, and that gives the hydrogen down. That would be a steric explanation. Hydrogenations normally only affect CC pi bonds. Notice that the carbonyl, the CO pi bond, is unaffected by the reaction conditions as shown. Problem number 3 does not have H2, so it is not a hydrogenation. The key reagent is MCPBA. That stands for metachloro peroxybenzoic acid. This is not a regular carboxylic acid. It has an extra oxygen. This is often written as RCO3H. It is a peroxy acid. These react with alkenes to make epoxides. Sure enough, our starter material has an alkene for this addition reaction. Our alkene should react with MCPBA to make an epoxide, a 3-membered ring with an oxygen. Here is the product, and here is the epoxide. Note that making an epoxide is a syn addition. Both CO bonds to the oxygen have the same orientation. In this case, both are down. Because the CO bonds are down, and let's add the hydrogens, in our starter material, both of the hydrogens will finish in the other orientation, both up. A natural question would be, why does the oxygen end up down? Why doesn't the oxygen add to the top face instead? Great question. In the previous problem, I tried to explain the stereochemistry through sterics. I said that a neighboring group was up, so because of sterics, the addition occurred on the bottom face. For this reaction, the neighboring group is down. If we're going to argue sterics, then we might expect the epoxide to be up, but it's not. Note that the nearby group has atoms like NH and oxygen that can engage in hydrogen bonds. It's possible that the MCPBA forms hydrogen bonds with this nitrogen group and delivers the oxygen preferentially from the same face, the bottom face. This explanation is conjecture, but factors like sterics and hydrogen bonding are often important for explaining stereochemical outcomes. Next question. Well, this starter material is the same as the product from the previous problem. We have the epoxide. Just about any time you make an epoxide, the next step will be opening the epoxide. Epoxides, as 3-membered rings, have a lot of ring strain. They react readily with nucleophiles, weak nucleophiles under acidic conditions, and strong nucleophiles under basic conditions. Over the arrow is our only reagent. I call this a carboxylic acid, but it's not a regular carboxylic acid because it has this SH instead of an OH. Whether a standard acid or not, it's acidic. The first step of this reaction is likely protonation of the epoxide oxygen. The conjugate base of the acid is this thing. It's a carboxylate with a sulfur in place of an oxygen. There are 2 resonance forms. I'm showing the one with sulfur as an anion because I know I need a good nucleophile to open this epoxide, and sulfur is more nucleophilic than oxygen. Great, we've activated the epoxide through protonation. This thing wants to be opened. We've also formed a decent nucleophile to do the opening. All we need now is to open the ring. I'm going to draw the reaction mechanism to make a new CS bond and break a CO bond. That gives our final product. Note that the nucleophile, when it opens the ring, must approach from the back face of the CO bond. So in this case, the nucleophile must attack from the top, and the new group, the new CS bond, will be up. The CO bond, which is unchanged, is still down. Based on this reaction I've shown, a completely reasonable alternative product would be to have the nucleophile attack on the other side of the protonated epoxide. That would form this product. These two products are regioisomers. Both of these are valid in theory. I do not have the original reference of this reaction. The reference at the bottom of the screen is a review, not the original work. The yield on this reaction is low, only 32%. It's possible that the original researchers obtained a mixture of these two regioisomers, but only wanted the first product that we drew. Reactions often give mixtures, and you must fish out the one you want and, likely, throw out the rest. Problem number 5. This looks familiar. We have hydrogen, H2. This must be a hydrogenation. Sure enough, we have a palladium catalyst among our reagents. This isn't palladium on carbon, it is palladium hydroxide. Actually, palladium hydroxide is also normally included with graphite. By appearance, PDC and palladium hydroxide look just about identical. We also have an alcohol solvent, super common for hydrogenations. Looking at our starting material, we see a CO double bond, the carbonyl, that won't react. The pi bonds in the benzene ring, those won't react. That leaves these two CC pi double bonds. The top one is actually part of a more complex aromatic ring. This 6,5 ring system is collectively called an indole. That leaves the lower double bond to do the reaction. Here is the product. There's not much to discuss about the reaction. It's just a typical addition of hydrogen to an alkene. Question 6. On the left is a starting material that is very commonly encountered in organic chemistry. This is called epichlorohydrin. It is an epoxide. What do we do to epoxides? We open them. Not surprisingly, above the arrow, we have a nucleophile that is strong enough to open this epoxide. Let's go for it. The nitrogen will attack the epoxide. Unless the epoxide is protonated, and it's not, the nucleophile will attack at the less substituted side of the epoxide. I'm going to draw the outcome of this reaction while taking some liberties with the hydrogens on nitrogen. What's interesting about epichlorohydrin is that when it gets opened, the O- leans over, kicks out the chloride, and reforms a new epoxide. Sometimes this is the final product. If you predicted that this is the final outcome, that would be completely reasonable. In this reference, however, the researchers continued to drive this reaction so that the nitrogen performed an intramolecular attack on the new epoxide to form another CN bond to make a ring. Here is the final product. Again, I've taken some liberties and moved around a hydrogen to get all the atoms back to no formal charge. This is kind of an interesting product to make from two very simple starting materials, epichlorohydrin and benzylamine. Problem number 7. This problem set is about addition reactions. So the key functional group of our starting material will be the alkene. There are other groups on this molecule. The silicon kind of stands out. Don't be distracted. We're here to do an addition reaction. And the alkene is where the action is going to take place. Over the arrow, we have a borane, a molecule with a BH group. This reaction will be a hydroboration, addition of a BH bond across an alkene. Under the arrow is something interesting, some kind of iridium catalyst. I admit this isn't a simple hydroboration, but we can treat it that way if we want. The product we predict will be the same. Okay, when we do a hydroboration, we need to worry about regiochemistry. The hydrogen will add to the more hindered side of the alkene. The larger boron and its groups will add to the less hindered side. This is driven by sterics. Based on this argument, here is the product. We've done a hydroboration and made a carbon-boron bond. I'm not focusing on the next steps, but normally hydroboration products set up another reaction, a transformation of the new carbon-boron bond. Last problem, and of course it is a hydrogenation. We have an alkene for the addition, and over the arrow is hydrogen. The catalyst is ruthenium instead of palladium or nickel or platinum. That's okay, lots of metals can catalyze hydrogenations. Based on what we said, and knowing that the addition of hydrogen is a syn addition, there are two products we could draw. Here they are. These two molecules are enantiomers of each other. Normally we'd expect to get a 50-50 mixture of these enantiomers, a racemic mixture, but we ignored something under the arrow. S-segphos. What is this? The S is a reference to stereochemistry. S-segphos is a chiral molecule that affects the outcome of the hydrogenation to favor one enantiomer over the other. In other words, this hydrogenation gives mostly just one of these products. Without additional knowledge, we can't predict which one is favored. But the favored molecule is the one on the left, not the one on the right. This is the major enantiomer. The use of chiral molecules like S-segphos to cause mostly one enantiomer to be formed from a metal-catalyzed reaction is very common in advanced organic synthesis. It falls within a field called asymmetric catalysis. I hope you enjoyed these problems and that they help you better understand addition reactions. Please subscribe to the channel, like this video, or leave a comment. Thank you for watching. Remember that links to these problem sets are in the video description.